Hello everyone, Mr. Fawcett here, and we're back with another geometry lesson. Today we are going to take our properties of similar triangles to real-world scenarios. Previously, we've just kind of looked at, proving triangles similar. We've looked at some different theorems involving similar triangles, and we've looked at some pretty basic diagram problems. Today you're going to learn how, some of these things are used outside of just a mathematical classroom, and how they can be applied to some real world ideas and concepts. So first thing we are going to do, we are going to look at the do now. Just quick unit conversions, because you are going to have a couple of those today, so just get some quick practice in. Do number 1 and 2. I guess this is not number 2. Let's make it a 2. And then come back and check your answers. Okay, so 6 feet and 3 inches to inches. Well, we know that there are 12 inches in a foot, so we have 6 times 12 plus 3, right? So 6 feet times 12 inches plus the extra 3 inches, that gives us 75 inches. 5 meters and 38 centimeters to centimeters. Well, for every meter, there are 100 centimeters, so 5 times 100 plus 38. And that's going to give us 538 centimeters. So when you're doing a problem, whenever you have multiple units, you're going to want to convert them to all the same units. You're going to want to convert them each. You're going to want to convert each set of units to the same units so that the math works out properly, right? If you're working with meters and centimeters, well, you're going to have that extra factor of 100 in there that you're going to have to account for at some point. So when you're first doing a problem, if you notice that there's different units throughout, generally just easiest to convert all of them to the same type of unit and then do the math from there. Okay. Indirect measurement. This is a type of measurement where you are not measuring the figure directly, but rather using formulas, similar figures, and or proportions to measure it. So for example, it may not be feasible to measure the height of a large building using a tape measure, but there are other ways we can figure out the height. And we're going to look at one of those examples below. All right, so it says Mr. Fawcett measured his shadow at 3 p.m. and found that it was 42 inches. He also measured the Sky Point flagpole shadow and found that it was 180 inches. If Mr. Fawcett is 72 inches tall, how tall is the flagpole? Convert your answer to the nearest tenth of a foot and draw a diagram to represent the scenario. So again, this is going to be a way where we're able to measure something very large, like a flagpole, where it's not very easy to just, take a tape measure to the top of a flagpole and drag it all the way down to the ground, right? You need a ladder, you need somebody to hold the ladder, and it's still pretty dangerous. Well, this is a way where we can all stay on the ground and still figure out the measurement of that flagpole. Let me draw a little diagram for you, and hopefully you'll start to see where the application to similar triangles is going to come from. So I'm going to first actually start with the sun. We have a sun, and it's going to shoot down a ray. Okay? I then have Mr. Fawcett. He is standing here. And I have a flagpole. We'll say that's up here. Not the best flagpole, but you get the idea. So right off the bat, hopefully you can see a couple of things. We have 2 right angles here, right? Because I'm standing straight up and the flagpole is standing straight up. That also means we have corresponding angles that are also congruent right here. Okay, so now this is where the 2 similar triangles comes in. We have one triangle right here in black, and we have one triangle right here in pink. Those are going to be similar by AA. Now we have to think about where are the shadows. Okay, well, the flagpole shadow is going to be this entire length. We know that's 180 inches. And we know that Mr. Fawcett's shadow is 42 inches. And we know one final thing that Mr. Fawcett is 72 inches tall. Again, diagram not drawn to scale, obviously, in terms of, that 42 inches may look longer than 72, but that's why we're labeling it. So if we have these similar triangles, right, we know that there's proportional relationships we can pull out. And let me just label this side as X, because that's what I want to find. I want to find the height of the flagpole. So pause the video. See if you can come up with a proportional relationship that would allow us to find the value of X. And maybe it would be easier if you separated these triangles, right? So you pulled them apart from one another and maybe label them individually. So if you want to do that, that's fine. That may help you see these relationships a little bit better. Okay, so if you did pull them apart, we have 42, 72, we have 180, and we have X. I'll just throw the angle congruency arcs in there as well. So if I set up this proportion, there's a bunch of different ways I could do it. I could do 72 over 42 is equal to X over 180. If I want to use the pink triangle completely on the left-hand side and the black triangle on the right-hand side, I could also do 72 over X is equal to 42 over 180. In that case, I'm doing my pink triangle in the numerator and my black triangle in the denominator. And there's some other ways too, right? You could flip those numerators and denominators if you flip both of them. But either way that you set it up, as long as it's a correct relationship, you're going to be multiplying the same things when you cross multiply. And let me just show you what I mean by that. All right, so if I do the green, in my cross multiplication ovals, I'm getting 72 times 180. Same thing if I do it over here, 72 times 180 and 42 times X. So many different ways to set it up. You're still going to get the same answer as long as you're choosing one of those correct ways. Now, an incorrect way, right, would be if I did 72 over 42 equal to 180 over X. Now, think about why that would be incorrect. Well, you did 72 over 42, which means the numerator of this ratio needs to be the corresponding side to 72, right? Because 72 and X are corresponding sides. So those would both have to be in the numerator or both be in the denominator if you're setting it up this way. However, we put the X in the denominator or the 180 in the numerator, which makes this an incorrect way of setting it up. So if you do it one of the correct ways, let's go back and actually solve it. 72 times 180, that gives us 12,960 is equal to 42x. Divide both sides by 42, and we get 308.57 is approximately equal to x. I'm using approximately equal because I had to round. Now, is that our answer? 308.57? Do I need to round differently? Do I need to convert? Let's think about it. Well, it says convert your answer to the nearest tenth of a foot. So I want to convert that 308.57 to feet and round to the nearest tenth. So I'm going to divide that number by 12, right? Because right here, this number is in inches. So dividing by 12 would convert it to feet, and I get 25.7 feet is approximately the height of the flagpole. So again, this would be something you could do by yourself, right? Because you would just have to stay on the ground to get all these measurements. So a cool way of, figuring some measurements out that may be hard to figure out otherwise, but using a little bit of similar triangle properties, we can do it fairly easily. Okay, I think we're going to skip the next few. We'll work on those in class. You can try those on your own. Again, in these diagrams, you're just looking for similar triangles. I know that in this Lincoln Memorial one, you're actually doing, it's not going to be similar triangles, they're going to be rectangles, but sort of the same properties apply based on similar polygons. We are going to move to number 4 though, because this is a new idea. All right. So it says, use the diagram below to answer the following questions. Are the triangles similar? If so, by what criteria? And what is the scale factor? So let's assume that this is the image and this is the pre-image. So go ahead, see if you could prove whether those triangles are similar, and if so, what the scale factor is. Okay, so both triangles share a right angle, which makes those two angles congruent. Now we need to see if they have two sets of sides that have the same ratio. So I'm going to compare 3 to 9. So to find that scale factor, I do 9 over 3, which is equal to 3. And I'll compare 4 to 12. So 12 over 4 is also equal to 3. Again, how did I know which sides to compare? Well, I compared the smallest sides of both triangles and the largest sides of both triangles. Put those in the same ratio. So we know these triangles are similar. Yes. Similar by SAS. Part B says find the lengths of the missing sides. So go ahead and see if you could find those, PR and WY. Okay, so hopefully we see that these are right triangles, so we just do a Pythagorean theorem. So we have PR squared is equal to 3 squared plus 4 squared. So I get PR squared is equal to 25, which means that PR is equal to 5. Whoops. For WY, WY squared is equal to 9 squared plus 12 squared, which means WY squared is equal to 225, which means that WY is equal to 15. And that makes sense, right? If PR is equal to 5, well, that scale factor we already know is 3. So we actually didn't have to go through the Pythagorean theorem again if we just use properties of similar triangles. But either way is okay. Okay, let's go and talk about C. Find the perimeters of both triangles. Does it have a relationship to the scale factor? Go ahead and answer that question. Pause the video and come back. Well, perimeter of triangle PQR, again, we're just going to add up all the sides. That gives us 12. Perimeter of WXY gives us 36. So, yes, there does seem to be a relationship between the perimeters with the scale factor. If we multiply the smaller perimeter by the scale factor, or the pre-images perimeter, we're going to get the perimeter of the image. So the scale factor holds true for the perimeters. The next question is going to ask you to compare the areas. Quick little reminder, area of a triangle. What is going on? 1/2, whoops, one more time. 1/2 base times height. So go ahead, find the areas of both of those triangles and just check to make sure that scale factor also holds true for area. Okay, so the area of the smaller triangle, this would be 1/2 times base times height, or 1/2 times 3 times 4. That gives us an area of 6. Area of the larger triangle, 1/2 times 9 times 12. That gives us an area of 54. So it turns out that the scale factor does not hold true for the perimeter, or at least not in the way we're thinking. However, there still is a relationship, right? If I look at these scale factors, I'm not multiplying by 3, but I am multiplying by 9. And it may be hard to tell with just one example here. So let me give you another one. It's always good to, before we write a conjecture, to test it in more than just one way. So let me give you 2 more similar triangles. We'll just do right triangles to make it easy. Let's do 4 and 5. We'll make the scale factor 4 this time. You know what? We'll actually make it 2. Make it a little easier. We'll do 8 and 10. So find the areas of both of those and see if you can then figure out how the scale factor plays a part. Also looking at the relationship between the first 2 areas. Okay, so the area down here, 4 times 5 times 1/2, which gives us 10. Area over here, 8 times 10 times 1/2, which gives us 40. So here, we multiplied by 4. Scale factor was 2. So compare both of these examples, and if we know the scale factor, is there a way to know how the area will be affected? And here we're not multiplying by the scale factor, but we're multiplying by the square of the scale factor. So notice up here, right, 9 is equal to 3 squared. Down here, 4 is equal to 2 squared. So when you're doing area, and this has to do with area being 2-dimensional, you're not going to multiply by just the scale factor. You're going to multiply by the square of the scale factor. And this holds true not just for triangles. This will hold true for squares, for rectangles, for hexagons, for pentagons, for any type of polygon. It's also going to hold true for circles as well, even though circles are not a polygon. So let's put this into words. So know to find the new area, we need to multiply by the square of the scale factor, not just the scale factor itself. Part E asks us to sum everything up. So it says, if we know the scale factor, how can we use it to describe how the perimeter and area will change? This is going to be an important box to know for future questions, quizzes, and exams. So the perimeter of the pre-image times the scale factor will give you the perimeter of the image. right? That's the same relationship as the sides. And that's because they're both one-dimensional, right? A side of a polygon is one dimension. The perimeter of a polygon is also one dimension. So you're just multiplying by the scale factor to find the new perimeter. The area, though, so if I'm trying to find the new area, well, it's going to be the area of the preimage times the scale factor squared is going to give me the area of the image. And you may say, well, why can't I just do the math to find the new area, right? Why can't I just use the area formula for that given shape? Well, sometimes you may not know the dimensions of the new shape. Maybe they just give you the old area and they say, if I enlarge this polygon by a factor of 4, what is the new area going to be? And in that case, you have to understand this relationship. You won't be able to, substitute in the dimensions to the certain area formula to find it. You have to understand the relationship between scale factors and area. We are going to stop the video here. We have gone long enough. We'll complete the rest of these problems in class. You can get started on them if you'd like. Other than that, have a fantastic day. And we'll look forward to seeing you next time, which will probably be a new unit.